we have the probability of defective as 0.1 and probability of picking a good component is the rest. So I can define it as 1 minus the upper value, so 0.9. Now we are making the sets 3. So n number of sets or the components in one set, right? Components in one set. So our variable x will be 0, 1, 2, and 3. It means the number of defectives, a set of 3. So there can be 0, 1, 2, and 3. And their probabilities, we will compute it by formula. So probability, this probability is probability x, such that x is equal to any of the values between 0 to 3. Okay. So now we have to, in our calculation, we require the factorials. So I write here, it is equal to NCX. So x value I will pick from here. So it is 3 factorial, n factorial as FACT, factorial of 3, then divided by factorial of x. So I can pick the value of x from its respective cell. See x factorial times factorial of n minus x, which is at D6 location. And then I have to give the powers. So times defective probability. Well, I can pick that one from its respective cell, $1. So the cell has been rightfully selected. It's raised to the power x. So x has been rightfully picked. And then for good raised to the power, good component, it is at $2 and raised to the power n minus x. So n is 3 minus x. X is at D6. That's going to be the calculation, right? Individual probability calculation. Okay. So there is some misbalance of the brackets, parentheses. Okay. So the number cannot be greater than 1. So we have to carefully see the calculation. So, okay. This one is over. And then x to the power e minus factorial of 3. Well, this should be completed here. Okay. Factorial, and this one. And not this one. So still there is an imbalance. Okay, 0.729. So the automatic correction is fine. The number is less than 1. Therefore, I am happy. So now I can repeat the same set of calculations for the other events. And now I can verify all the numbers are less than 1, but the total probability is 1. So I can test that. Do the summation for all the probabilities. So it's 1. It means the calculations are correct, right? The same thing is possible from the default Microsoft Excel functions. So I can write here the same calculation. It is equal to binomial distribution is available in Excel. So I see binomial dot distribution, and it requires the number to be provided. So the number is x. Then the number of trials. The number of trials are 3. So I can pick that from its respective number. Then the probability. The probability we have to provide for the defective $1. So that has been rightfully selected. Then there is another option, two options. Whether you are interested to calculate the individual probability, which is the probability mass function, or you are interested in computing the cumulative distribution, right? In my problem, I have computed the probability mass function, probability of individual event, probability of 0 defective, probability of 1 defective, right? So I select false. So you can see the word, it is to generate probability mass function, individual probabilities. So it means we have done it right way. We have done the right way. The calculation of factorials has been programmed in the binom function. If you go for the cumulative calculation, so cumulative distribution function, so it is the first value as it is, right? And at next level, you are going to add the current value with the previous value. So it will rise up to a higher value and it will ultimately saturate at 1. The same thing in Microsoft Excel. Write the function binom dot distribution, and again the number of trials, number x, the number of trials as $4, the probability from $1, and now write here true with the correct spellings. So first number is the same and remaining probabilities will be added. So that's the fair expression, right? So you can do the plotting. For example, the density function, I plot it with the columns. Select data option, add a series. Series values are only the y values. The probability of individual events. And at x-axis, not from 1 to 4, our axis begins with the 0. Our events are 0, 1, 2, 3. So that's going to be the distribution shape, right? So you can provide the axis, the options. And now the beauty of doing things on computer, if the probability of defectives is higher, say 0.2, so everything will be changed. Everything will be automatically taken care. So first, the defective B probability was updated as 0.8. Number of tries are same, and the probabilities are computed, they are updated. Now in the same thing, if we check the problem of tossing a coin, so in that case we have the probabilities 0.5. So you can see that the probabilities of the higher values, they tend to grow and then they tend to decline. So there is going to be a symmetry in binomial distribution if you have equal probability. If you have low probability of finding the desired event, then it has a peak towards the left, towards the smaller values, right? And if you have the condition upside down, you will find that the peak is shifted towards the other side. So that's really the beauty of binomial distribution. And therefore, the first distribution that we learn is the binomial distribution. Okay, let's stop at this point for the demonstration. The lecture will continue.